Okay, so let me introduce our first speaker is Dr. Eric Young. He is a research soil scientist with the USDA-ARS Institute for Environmentally Integrated Dairy Management. In 2018, Eric joined the ARS lab in Marshfield, Wisconsin as a research soil scientist, where his research focuses on optimizing nutrient efficiency and foraging cropping systems. Thank you, Eric, for joining us today, and I'll turn it over to Eric to present. Thank you.
Thank you, Laura. Now I should be able to just share, correct? Okay. Can everybody see that okay?
That looks great. Thanks, Eric.
Okay, super. All right, well, thanks again for the invitation to talk this afternoon. I appreciate it. And I'm going to be sharing some research that was recently published a couple of months ago. This is a big group effort here. You can see the co-authors listed here. Jessica Sherman is my research technician here in Marshfield, and Brooke Bebenek is a graduate student with Randy Jackson in the Department of Agronomy. And Randy Jackson, I think probably most of you all know. Jason Cavadini is formerly the agronomist up at the MARS facility, but now he is the statewide extension grazing specialist. And then Matthew Akins is our research leader, and formerly with UW Extension for a number of years. So anytime I talk about grazing or any kind of water quality, I like to talk about the importance of the cropping system. So I think it's pretty self-explanatory, but it really is a large driver of some of the overall trends that we see, such as erosion and particulate phosphorus loss, things like that. You know, going from an annual system such as a corn silage system that's tilled or has some level of tillage annually, versus perennial forage stand or a grazing system where we have year-round ground cover. So those are two big drivers, and we tend to see more dissolved nutrients in perennial forage systems versus more particulate losses in annual systems, particularly with corn silage. So just a little bit on edge of field water quality. That's the approach that we used for this particular study. And sorry if this is review for some of you, but so for edge of field water quality studies, we're really interested in measuring field scale losses in the field. And oftentimes we'll use a paired watershed approach, but not every time. So in this particular study, we applied a paired watershed study, which consists of two periods. The first being a calibration period, where all the experimental units or sub watersheds are managed identically, and then followed by a treatment phase where some number of the fields are treated differently than they were during the calibration period, and then the control field will remain under that same management during the treatment phase. And that's how we're able to assess statistical differences between the treatments. So with most of the edge of field water quality programs here in Wisconsin and Northeast and across the U.S., the idea is to monitor runoff year-round. And this can include surface runoff and or tile drainage, sometimes both. And the other important aspect is tracking the farmer practices. So we need to know, manure management, what the cropping history is, fertilizer inputs and everything like that. That's a really key component for these types of studies, so we can help explain the observations. And as I said, the paired watershed analysis is common. And of course, UW Discovery Farms has been a leader in this research, certainly in Wisconsin. And so I put them down there because of that reason. So they've just done a tremendous amount of excellent work in this area. So without further ado, just a little background on the study location. It's the Marshfield Agricultural Research Station in Stratford, Wisconsin. It's about 10 miles north of Marshfield. And for this particular study, the calibration phase was a little bit longer than the treatment phase, but that occurred from 2013 to 2018. And during that time, all 4 fields were managed as a grass with some legume. It was originally an alfalfa field, but it doesn't hold alfalfa very well. So it was mainly just meadow fescue and legume. And then the treatment phase occurred from 2018 to 2020. And you can see the 4 fields there. I'll talk more in depth about those as we go on here. And this is a little busy slide here, so I apologize. As I mentioned, the hay field was mainly meadow fescue with a white clover. This field was cut 2 to 3 times per year and received about 5,000 gallons per acre or 47,000 liters per hectare, if you prefer. The continuous stocking treatment, these animals had unrestricted access to the pasture, and you can see the average weight there and stocking density. And there were 5 dairy heifers for each of these treatments. The permanent paddock stocking system will be abbreviated PPS. And this consisted of the pasture being divided into approximately 3 zones, and with temporary fencing, and they were moved every 10 to 15 days, depending on the regrowth. And then finally, we had the adaptive management paddock stocking, kind of a mouthful, and we abbreviated that as AMPS. And in this system, paddocks were established large enough to support about 1 to 3 days of grazing. Again, this really depended on the time of year and rainfall, etc. Okay. So just quickly go over some of the measurements that were included in this study. So obviously we measured runoff year round, and below you can see the flumes that we use. These are fiberglass H flumes. So we had 1 flume per watershed in the low corner where all of the surface runoff would drain to, and you can see we had wing walls. Also, I should mention that each field was bermed. These watersheds have been in existence since 2007. Sorry, I want to mention that from the outset. And originally, USGS helped install these. So these fields were bermed to be hydrologically isolated. So we also measured suspended sediment, total nitrogen, ammonium nitrogen, nitrate N, and organic N by difference, as well as total phosphorus, dissolved reactive P, and then particulate organic P by difference. We also monitored daily weather and also made estimates of the amount of phosphorus and nitrogen applied from dairy manure for the hayfield, as well as what the heifers excreted during the growing season based on UW Extension publication. Okay, so we'll jump into some results here, because I know I just have maybe 5 or 6 minutes left here, so I'm going to have to kind of hustle. So you can see from the left panel here that in general, the weather during the calibration and treatment period was cooler and wetter than normal. And then on the right-hand side, we have a quick summary of the nitrogen and phosphorus inputs for the grazing system compared to the hayfield, and then I have it broken out by calibration and treatment period. So here in 2012 to 2017, right, you can see quite a bit of nitrogen, over, pushing 170 pounds, or sorry, 170 kilograms per hectare of total phosphorus. I'm sorry, total nitrogen. Sorry about that. The green is nitrogen. And the orange bars are total phosphorus. So definitely getting more nitrogen than phosphorus in these fields. during the calibration period. But I just want to point out that there are some differences between the hay fields and the grazing systems, obviously, right? Because we're applying liquid dairy manure versus what the animals are excreting, and that'd be very difficult to match. So that was expected, but just something to keep in mind. Okay, we'll jump into another kind of busy graph here. This figure is showing runoff volumetric runoff in millimeters of each grazing system compared to the control. And you can see in general, there's quite a substantial increase during the treatment phase. So the orange squares represent the grazing phase, and the blue diamonds represent the calibration period. And you can see compared to the control, each system each grazing system increased a surface runoff compared to when the field was managed as a hay field. And we think that's probably likely related to the foot traffic of the animals, particularly during wetter times where we can, develop compacted conditions. And then the bottom panel here on the right, you can see the cumulative difference or cumulative loss in runoff in millimeters during the calibration and treatment phase. And just want to point out the yellow circles there is the continuous, which is continuous grazing, which is abbreviated CS. You can see that kind of jumped up fairly quickly there in 2018 to the end of the study. So something to keep an eye on there. Okay, so now we'll jump into a somewhat busy table, and I apologize, but I'll try to keep this straight for everybody. These are actually means. So these would be means during the calibration and treatment period. And they're based off their regressions, but they're actual event means. You can think of them as so for runoff, you can see, as I was just talking about, the PPS and continuous both had significantly greater average surface runoff losses than the control. So and that was sort of indicative from those regression plots that we looked at. And just real quickly here, these p values here. So P1 tests for if there's a difference between the calibration and treatment period mean. And then the P2 is testing whether the treatment mean is different than the control mean during this phase. So that's what the P1 and P2, and then P3 and P4, don't worry about, pretend they're not there. They're for slope and intercept, but I'm not going to talk about those in the interest of time. So taking a quick look at the sediment results, you can see that the continuous treatment had significantly higher average event sediment concentrations, suspended solids, if you want to think of it as that, than the control. Taking a quick look here at ammonium concentrations and loads. So for ammonium concentrations, we didn't see any real significant differences. You can see here, no significant differences NS here for the both between calibration and treatment period means, and as well as differences between the treatments, the grazing treatments, and the control watershed. Well, however, if you recall, we did see that increase in surface runoff. So when we calculated loads, we did see some significantly greater ammonium nitrogen loads compared to the control treatment. So taking a look at cumulative losses here, again, this is cumulative ammonium on the left loss, and then cumulative total nitrogen loss on the right-hand panel. These are have somewhat similar trends in that the continuous stocking treatment was well above the other treatments, both in terms of ammonium and a total nitrogen loss, you can see here. Now, we didn't really apply statistics to this like we did the averages. I suppose one could do that, but we didn't do that for this paper. But I think these numbers kind of, in my mind, kind of speak for themselves. Okay, well, another quick table here. So this is looking at total and dissolved reactive phosphorus. So total phosphorus concentrations, we did see some differences both between the treatment and calibration period. You can see here, and then also some differences between the treatments and the control as well. Although they're kind of close, but statistically there were some differences. And then looking at DRP, we saw somewhat larger differences between the control and the treatment watersheds. So for example, here, the PPS system had significantly lower DRP concentrations than the control, right? 0.7 versus 1.2, whereas AMPS and continuous had fairly similar concentrations. Real quick, looking at total phosphorus and DRP cumulative losses, a little bit closer values here between the continuous and PPS and the AMPS. One thing I wanted to point out here with the AMPS treatment, so this was the most rotationally intensive treatment, right, where the heifers were rotated the most. And you can see we had a lot less total phosphorus and DRP loss in this system. Now, one thing I want to point out is that also had the lowest runoff. So it was not always like statistically significant because it had the lower runoff kind of driving those phosphorus load differences. But again, we did see much lower losses from the AMPS system. Okay, taking a quick look here at efficiency, we basically calculated the amount of nitrogen and phosphorus lost as a percentage of what was applied from the heifers or the dairy manure over the study. And you can see that the AMPS was by far the most efficient. So per unit of applied nitrogen and phosphorus, it lost the least. You can see that. And then we also did measure yields, Brook measured yields, I should say. And basically, we found that the continuous had the lowest yields, not surprisingly, because it's getting trampled more, and it doesn't give that forage enough time to sort of regrow before it's trampled again by the animals. Okay, so real quick, the continuous stocking led to greater runoff, total nitrogen and ammonium loss, as well as greater DRP concentrations than the control. The AMP system had lower losses and PPS similar to losses to the control. And real quick, this is an active area of research here. We're currently working with Laura Good at UW on the phosphorus index and calibrating that to our watersheds up there. So we're doing that, as well as trying to hone in on how to better estimate daily phosphorus losses, including during the winter. So I'm sorry that took longer than I thought, and I hope I left enough time for Kelsey.
Yeah, great. Thank you so much, Eric. Really interesting research. So no problem to go over time to share. Yep.
Sorry about that.
Nope, that's okay. We're going to pause here just for a moment to launch a quick poll to collect some demographic information from you guys. So this anonymous information helps us to evaluate audiences and who we're reaching, and it helps us just to do some self-assessment and kind of how to rate. So let's hopefully launch this poll. All right. Okay. Hopefully you guys can see it now. As you're doing this, just a heads up, there will be another question or two questions, I believe, as you exit the webinar today. So after Kelsey's presentation and after the Q&A, and those two questions, again, just help us as a program self-rate and see how we can improve future programs. So just a heads up, as you leave the webinar, those two questions should pop up automatically, and we appreciate any participation for that. Okay, and as we're waiting for the poll, I see Kelsey's popped up her presentation. So I'll introduce our next speaker is Kelsey Hyland. She is an outreach specialist with our ag water quality program in the Division of Extension at UW-Madison. She's located in the northwest of the state. So I think I can end this poll and hand it off to Kelsey.
Can you see the screen all right?
Yep, looks great.
Okay, great. Well, thank you everyone for joining us here today to talk about some grazing and water quality. And thank you to Dr. Young for sharing that interesting research. I just want to start this presentation by saying that this is a really huge topic that could probably be broken down into a lot of different presentations. So today we're just going to be kind of taking a 10,000-foot overview, but if you're really interested in a specific topic or feel like I missed something, feel free to shoot me an email and I would love to talk more about it with you. So we'll set the stage by first talking about Wisconsin's two grand water quality challenges, phosphorus and nitrogen. And if you listened to the webinar 2 weeks ago with Chelsea and Jamie, you would have heard that phosphorus is Wisconsin's #1 water quality pollutant. And this is because phosphorus is often the limiting nutrient in most of Wisconsin's aquatic ecosystems. So even a little bit can kind of wreak havoc on the ecosystem, leading to eutrophication, harmful algal blooms, and sometimes subsequent fish kills. And I'm actually not going to be talking about nitrogen today. While I was preparing for this presentation, I had slides for both, but I felt like I couldn't do either justice if I talked about both. So if you want to learn more about nitrogen, maybe that can be a plan for next year. But when we think about the relationship between grazing and pasture and water quality, grazing and pasture systems can have many protective benefits, but this relationship is not automatic. It's mediated by a lot of factors like stand height, biomass, duration of rotation. And don't get super overwhelmed by this list because we'll be going through each of these today or most of them. But really the point here is that in any natural or agricultural system, none of them are perfectly closed, so some nutrient loss is inevitable, but really our goal here is how do we make the system less leaky? And to do that, we really have to understand how phosphorus and other nutrients move through grazing systems and maybe how that might look a little bit different systems. So if you watched that webinar 2 weeks ago, or you've interacted with the phosphorus cycle at other times of your life, you'll know that it's quite complicated. So for the sake of today's presentation and kind of taking a 10,000-foot overview, I created this really simple graphic we'll be referring back to today. And the main point of this graphic is for water quality impacts to happen in grazing systems, we need to have both a source of those nutrients and a transport mechanism like rain or snow. So first we'll kind of zero in on one of the sources of phosphorus in pasture systems, and those are the pasture plants themselves. So when pasture plants die and decompose, they can release a little bit of phosphorus into the system. And similarly, when pasture plants undergo freeze and thaw cycles, this can cause cells to burst and release some phosphorus too. The magnitude of this can kind of depend on the plant. So brassicas tend to release a little bit more than grasses and legumes. And Chelsea and Jamie did a really in-depth description of this 2 weeks ago if you want to go check out that webinar. But generally, these phosphorus losses are pretty low and not really something you can manage for beyond fine-tuning your species selection to kind of fit all the needs of your pasture. But one of the things you can manage for is appropriate stand height to really maximize your erosion control. So it's often helpful to think about above ground biomass as kind of a mirror to what's happening below ground. So when pasture plants are consistently overgrazed, this can reduce the carbohydrate stores and physically reduce those roots, affecting their ability to uptake nutrients and water, ultimately affecting that above ground canopy too. And this is very troublesome because we know that we need those strong root systems to hold onto soil so it doesn't get lost in runoff. And similarly, we need that really robust above ground canopy because that helps intercept raindrops so they don't dislodge soil particles that could ultimately be lost in runoff. So managing for stand height is species dependent, but generally grazing to about 4 to 6 inches will really promote regrowth and resilience of that pasture. So a good rule of thumb is to take half and leave half. And in Wisconsin, we do have some really good evidence of these benefits. So this is some data from Discovery Farms. And granted, we don't have a lot of pasture data, but this still tells a really nice story that on the vertical axis, we have soil loss here by pounds per acre. And on the x-axis, we have a comparison of different cropping systems like corn, corn silage, and pasture. And what you'll see in the pasture system is that our soil losses are really quite low, especially when we're maintaining that good stand height. And when we compare that to other systems like corn silage, which are getting close to that 50,000 pounds of soil loss, a really large number. This is because that's one of those crops that's harvested pretty early. And especially when you don't have cover crops in these systems, you're leaving that soil vulnerable to runoff for kind of an extended period of time. And controlling for erosion is not only important for keeping our soil, but also for controlling our particulate phosphorus losses, or the portion of phosphorus that is bound to soil particles. So you'll see that this graph on the vertical axis, we're looking at particulate phosphorus losses in pounds per acre, but you'll see that this kind of matches the trend we saw in the last graph. When we're controlling our soil, we're also doing a really good job of controlling those particulate phosphorus losses. So now if we move on to another source of phosphorus in the grazing system, this would be the manure from animals. So this can be a rich source of both nitrogen and phosphorus, but kind of for today's purpose, we're just talking about phosphorus. So to minimize water quality impacts in grazing systems, it's really important to distribute this fertility to really promote uptake by plants. And one of the ways to do that is rotationally grazing and being mindful of that stocking density. We also know that animals tend to congregate around bales, waters, and minerals. So it's important to rotate those as well. And I also have shade on this list because while you can't physically pick up and move a tree, you might be able to get creative with your grazing system, maybe putting waterers on the opposite side of trees to really promote some more homogeneous cover of that manure in your grazing systems. So another source of phosphorus in the grazing system, and a potentially underlooked one, is the soil itself, which can be a really rich source of phosphorus, especially in our Wisconsin soils. And sometimes this can have an overriding impact on source contribution to water quality impacts. So in some systems, it might be more graphically accurate to represent source contribution, something like this. So what do you do if you have soils testing high in phosphorus that you think might be contributing to some of these water quality impacts? This would be an important time to really consider some phosphorus drawdown strategies. And this would include reducing manure inputs on high soil test phosphorus fields. So that means keeping animals off of those fields and in conjunction with focusing hay harvest on these fields. And if at all possible, taking that hay harvest and trying to sell it off farm, because this will really help with your nutrient exports and your kind of overall phosphorus budget. Another creative approach that's not going to work for everybody, but maybe for some, would be to partner with another farmer to graze their cover crops and or corn stover, kind of get nutrients to a lower testing field. While you're not going to get great yields off this can sometimes help to extend the grazing season and kind of every day that you're not feeding hay is really an opportunity to save some money in your system. So this can be kind of a win-win situation. These opportunities exist after early harvested crops. So on the right here, we have a corn silage field, but this might also work after things like wheat. But in this process, it's really important to be realistic with goals because of the great buffering capacity that soils have. Phosphorus drawdown can be really slow. For example, a typical corn crop removes about only 3 to 5 parts per million of phosphorus a year. So next we'll focus on the last source of phosphorus in a grazing system we're going to talk about today, which is mineral. So phosphorus is an essential macronutrient for animals, but we know that when it's supplemented above an animal's need, that it can end up increasing in manure. And this is kind of both an environmental and economic concern because phosphorus is one of the most expensive nutrients to feed. And also if we have increased rates in manure, it could also be at risk for being lost. The good news is that generally Wisconsin's forage does contain adequate amounts of phosphorus for animals' needs. They did some pretty extensive sampling in the Chesapeake Bay area, and they found that 70% of the forage samples met phosphorus requirements at a cattle's greatest need, peak lactation, and then 99% of samples met their nutritional need at every other life stage. And for the Wisconsin purists, there was some research done here too in Holstein steers showing that when phosphorus was supplemented above cattle's need, it didn't lead to any additional weight gain. So kind of really no benefit to supplementing phosphorus beyond animals' need. So soil test levels can be kind of a fair indicator of phosphorus in your forage, but really to get an accurate picture, you want to make sure to test your forage. And this would include testing fresh forage and also hay, because depending on the maturity of the plant, the phosphorus content can vary, and you want to make sure that your animal's needs are being met throughout the year. If these P nutrient requirements are met, you can consider choosing mineral with low or zero phosphorus. And I know that it's pretty popular to use custom mineral mixes too, though, so this might be a good chance to kind of connect with your supplier and see if there's maybe some phosphorus in there. So the next piece we'll talk about is transport, which is difficult because, we can't necessarily control the weather, but we can identify when vulnerable times are and manage accordingly. So every year is going to be a little bit different. This year is a great example, but generally when we look at the research, some trends do emerge. And these show us that the majority of runoff losses in pasture systems really happen during that non-growing season. So this graph on the left is from some water quality monitoring data done in Southwest Wisconsin. And the top is looking at precipitation, and the bottom is looking at runoff. And what we'll see is that even though precipitation peaks during that summer period, we really see the peak runoff happening in our winter months and kind of early spring around that March period. We likely see this for two reasons. So March is part of that non-growing season. We might have some frozen soils still, depending on the year. We can also have pretty saturated soil conditions because we know plants aren't actively growing, so evapotranspiration isn't happening, and we're getting those back-to-back rains. The soil can become saturated. When it has no place to go, it will run off. Then when we're talking about our winter vulnerable time, we might be dealing with some frozen soils, especially if we get that concrete frost, which is where the water in the soil pores, especially at the surface, are all frozen, essentially functioning as concrete, creating really ripe conditions for our runoff. So because we kind of know when these vulnerable times are, it's really important to avoid grazing hydrologically sensitive areas, especially during these times. So that would include fencing cattle off from, or animals that you're grazing off from riparian areas and stream banks, kind of concentrated flow areas, which we're seeing in the center photo. And this might also help to ease some compaction issues, which can reduce infiltration, increase runoff. We know that's really common when animals are having access to really wet soils. But ultimately, you know your land best, or the producers you're working with know their land best. So it's really important to pay attention to where water is flowing after large storm events or in that spring snow melt to help identify where these hydrologically sensitive areas are on farm. So from the research we talked about before, we know that when we're managing for good stand tide and practicing that we're doing a really good job of controlling our particulate phosphorus losses in our soil loss. But what about this dissolved phosphorus piece, or the portion of phosphorus that moves with water? And what the Wisconsin research tells us is that about 80% of phosphorus losses in grazing systems are in the dissolved form, which again makes sense because we know we're controlling that soil loss. Most of these are happening in the winter or non-growing season. And this is troublesome because a lot of these monitored dissolved phosphorus concentrations are often above water quality eutrophication levels. So a lot of times we're likely to be seeing these losses in areas where high P source is overlapping with high transport. And this is really common to see in our outwintering areas because we're dealing with some of those difficult transport conditions like frozen or wet soil, which might be leading to some increased compaction or increased runoff. And when we're pairing that with less frequent or no rotation, which is often the case in our outwintering areas, and concentrated manure and urine deposits, which might lead to a soil test phosphorus buildup, especially if we're using the same area from year to year. And in these outwintering areas too, we're also feeding hay. And a lot of times this hay might be imported from other farms. So you're adding just even more additional phosphorus into your system that can be at risk for loss. So this theory is great, but what does this actually look like on farm? So we'll take a look at a case study that Discovery Farms did, looking at some of these more challenging transport and high source conditions. So first I'll draw your attention to the K5, K6 pasture. And so K5 was looking at surface runoff and K6 was looking at tile monitoring, but these were both from the same area that was primarily grazed on frozen soil conditions or wet soils. So we know we have those tricky transport conditions. We know here we also had some pretty high source levels. So if you look at this table, this is just looking at that K5, K6 pasture, and they did some soil tests for 3 years of the monitoring period from 0 to 6 inches. And you can see that the soil test levels were quite high, much higher than the 42 parts per million that UW recommendations consider excessively high, where you kind of be in that drawdown phase with no additional inputs required. And that's for low organic matter soils too, so we're kind of even taking the more conservative, excessively high. So these levels were far above in those 0 to 6 inch samples. And even more troubling when we look at the 0 to 2 inches, we can see that the soil test phosphorus levels are sometimes almost double, but much higher, increasing risk. And we know this is increasing risk because the surface of the soil is really the portion that's most likely to be interacting with runoff. So just kind of an increased risk factor there. And another source condition of this case study is there was really high stocking density in that K5, K6 pasture. So that's kind of depicted in that dark navy blue there. So that was much higher than the transition paddocks or the paddocks used in summer. So when we put these high source and these high transport conditions, we do ultimately get higher losses. And I apologize, these graphs are a little old and a little fuzzy. We didn't have time to remake them. But this graph here is showing phosphorus yield on the left, so pounds per acre. And what we'll see is that in that K5, predominantly used in the winter pasture, we're getting pretty high phosphorus losses at about 4.5 pounds. And there's a popular saying that about 1 pound of phosphorus is equal to 500 pounds of energy. And while that's kind of oversimplifying it a bit because other things come into play like temperature, et cetera, it just kind of shows us that a little bit of phosphorus can go a long way in these aquatic ecosystems. So really want to reduce phosphorus where we can. So these 4.5 pound loss is a little high. This graph is also showing us that the majority of losses is happening during that frozen time period, which is kind of depicted by that light pink. The data also shows us, this one is also looking at phosphorus yield on the y-axis, but what this one shows us is that in those K5 pastures, the majority or the dissolved phosphorus losses are kind of peaking in that March time period. And that's again because soils might still be a little bit frozen or saturated. And then lastly, another phosphorus graph, which is also on the vertical axis. And this is just kind of showing that the majority of losses were in that dissolved form. And this is actually true for the transition paddocks and the summer paddocks, which you'll see farther on the right of the graph, but definitely we see the greatest magnitude of losses in those outwintering areas. So while this is not representative of all grazing in Wisconsin, it just kind of tells a story that when we have these really high source conditions and these high transport conditions, we can get higher losses. And anytime we add more risk factors to this equation, or we kind of increase the magnitude of those conditions, we're at risk for higher losses. So what are some strategies to reduce risk in outwintering areas? I had to save this photo for last too, because this is my sweet dog and my friend's sweet dog, who I noticed was on the call. So happy to have you here. But some strategies to reduce P risk in outwintering areas is to choose areas with low soil test phosphorus, setback from surface waters or concentrated flow areas, try to use a more conservative stocking density in these areas, and rotate from year to year to avoid P buildup. So I just really want to emphasize, like, sometimes these outwintering areas can be contributing up to 60% of total farm losses. So these are really critical areas to manage that P source. So now to go back to that first question I posed, how do we make the system less leaky? And really to do that, we have to manage for both source and transport, paying special attention to those areas where high source and high transport conditions overlap, which is often the case in those outwintering areas. And here is our contact information and a CCA credit if anybody needs it. Thanks for tuning in.
Great. Thank you so much, Kelsey, for that presentation. And again, thank you to Dr. Eric Young. So we can, as we kind of get into the questions, I think, oh, there's the CEU scan code for your 1 credit there. If you can scan that code, and if you can't, you can enter your CCA number into the chat box and we'll submit that on your behalf. Okay, so some questions. I have a question specifically for Eric's study. So based on your study, Eric, can you give a range about how much grass biomass you would think you would need in a paddock to help reduce those dissolved nutrient losses? Is there kind of a range that someone would shoot for grass cover?
Yeah, that's a good question. I think, as Kelsey pointed out, we want to maintain a certain sort of, not stubble height's the right word, but we don't want to overgraze, down to say 2 or 4 inches or something like that. I think leaving, 4 inches or so minimum is probably something, so I can't give you a tonnage or a biomass, but maybe more like a height. And I think we found that in the literature too, and doing some of the literature review, that once you get below that stubble height, then you run the risk of increasing erosion losses.
Great, thank you.
Yep.
And this one might be better aimed towards Kelsey. Are there best management practices for phosphorus loss different? Are they different in continuous grazing systems or rotational grazing? Or are these best management practices kind of just across the board what someone should use in all systems?
I think they definitely work across the board, but I think in some systems, when we're talking about managing for stand height or distributing fertility, I think those are probably more achievable in those rotationally grazed systems. So that's kind of a tool to get you there, but definitely best practices like managing for your source can be done in any system, because we know we're not really rotating cattle during the winter or other animals. So
Yep, great. We had a great question in the Q&A box, and I welcome any and all viewers to continue to ask questions in the Q&A box. This question was, if a pasture treatment reduces runoff volume and associated nutrient loss, does that mean more nitrogen, for example, is lost to groundwater if it's not running off the field, or what happens to that nitrogen?
Could you repeat the question?
Sure. So I think, yep. So if a pasture treatment reduces runoff volume,
Yep.
And the associated nutrient loss, I guess what's happening if that nitrogen is not running off, does that mean it's being lost to groundwater?
Right. So no, that doesn't necessarily imply it's being lost to groundwater, because there's other fates that nitrogen can take. Specifically in these soils, they're pretty dense and somewhat poorly drained. So I think we actually get we certainly get N2O losses, but we also get some denitrification losses as well, though we're not measuring that. These are pretty low. We see fairly low nitrate, for example, when we look in corn or these hay systems. So the nitrate, I mean, I'm not saying there's no nitrate leaching, but I would think by retaining more on the field, more runoff on the field, that does not imply that we would increase the nitrogen or phosphorus leaching, without we would need some more measurements to kind of look at that. But that's a good question. Yeah,
Absolutely. As usual, the more research is needed
that's
answer.
right. I didn't say it. No.
Yeah. Great. Yeah, thank you. I guess we can just wait a couple more minutes if some more questions come in. A good question we have. So looking at soil type, would soil type change nutrient losses in these pasture systems in any way? Is that a big factor?
Yeah, that is a big factor, and that's a really good question. Soil type absolutely has an impact here. In multiple ways. both in terms of the pasture productivity, but also in terms of the soil properties, specifically drainage, and the chemistry as well. That's going to be variable across the pastures. That's something we're looking into right now. We took a bunch of grid cell samples across the pastures because we're interested in that very question. So how do differences in soil properties, slope, drainage, pH, chemistry, phosphorus, how does that impact losses, in terms of desorption to runoff water and things like that?
Great. Yeah, great. Well, thank you. Like I said, maybe we'll wait for a couple more minutes for some questions to pile in. And again, I want to just thank our speakers one more time, Dr. Eric Young and Kelsey Hyland. Thank you for asking some questions, and please feel free to keep bringing them to the chat box. We did help. Just another question came in. Do these patterns apply for other ruminant livestock, or here we're just kind of talking about cattle?
Kelsey, I can take a quick stab at that. I think in general, yes. The basic principles of the grazing system and rotational versus continuous. I found that does kind of translate across systems, like, for example, for sheep and other and goats and other ruminants as well.
Yeah, I would agree. I think even for annual cropping systems, this idea of like a source and transport kind of holds true, but there might be like some specific differences. I'm not a nutritionist, but needs may vary between cattle or sheep or goats. So kind of some of those more specific nuances may change, but that kind of overall just how losses happen in cropping systems and pasture systems, I think would hold true.
Great. And we had another question come in. How does the type of grass species affect nutrient losses? So are some grass species better, quote unquote, better than others in lessening nutrient losses?
That's a really good question that I don't have a straight answer to. I do think this grass species probably has some impact, for sure. And both in terms of what Kelsey was talking about, how vulnerable it might be to freeze thaw and cell lysis and loss of phosphorus that way. But also just in terms of uptake and how phosphorus uptake, and also how it just impacts the soil properties, and how does it withstand foot traffic or the hoof traffic and stuff like that, trampling. So I would think that's pretty important, and I think that's probably something that needs to be looked at more. We couldn't look at that, unfortunately, in our setting, but
Sure.
Yeah, I would agree. I don't have a specific species and things, but I'm thinking of those crops that are really like deep rooted, I think would probably really help with some of that erosion control. But yeah, that's definitely something to look in for like specific species and dive into some more of that research.
Sure. Well, great. Thank you. Thank you all for your time and two great talks to really get our mind thinking of all these great questions and more research that Eric, you can do in the future. So of course, never ending, which is a good thing. But okay, I guess I could wait another minute or two for some more questions. But again, I'd like to thank all of our viewers. Again, this was the last of our 4-part webinar series, and all of the recordings will eventually be up on our topic hub on our YouTube channel. We appreciate everyone's time, and have a great rest of your day and enjoy this nice weather. And again, a reminder, as you close out of Zoom, you should get a 2-question little survey. If you don't mind quickly filling that out, we would appreciate it.
sounds good.